Okay, so we have been talking about electrokinetics. We finished our discussion on electrokinetics. Now let us look at microfabrication techniques. So in microfabrication techniques, we try to understand the different techniques available to fabricate microfluidic devices. We would start our discussion on talking about silicon based fabrication, because that is where the fabrication, the microfabrication originated from semiconductor microfabrication, and then we would also cover polymer and other substrates. Okay. So before we start our discussion on fabrication techniques, let us look at some of the materials that are available for microfabrication. So the materials that are available for microfabrication are silicon, polymers, glass, ceramics and metals. Okay. And the choice of selection of a metal would depend on the application that we are interested in and the fabrication techniques that we want to follow. Okay. So if you look at silicon as the material, silicon is most widely used because it is widely available and it has the capability to get integrated with IC, okay, integrated circuits. And the fabrication process for silicon is also very well established because that is the material that was used in semiconductor fabrication. Silicon has got interesting mechanical properties. It has got very high strength that is comparable to the steel, and also the elastic modulus. Silicon has also got good hardness and low density. So density of aluminum of silicon is typically less than that of aluminum, and silicon also has got low thermal expansion coefficient which makes it suitable particularly for sensor application. Okay. However, silicon is relatively complex and is expensive to produce, and it may have some biocompatibility issues. Okay. On the other hand, polymers, in polymers we are using substrate like PDMS, PMMA and COC. PDMS is polydimethylsilane and PMMA is polymethyl methacrylate, COC is cyclic olefin copolymer. Okay. So polymers are produced in large volumes and they are economical. The price of the polymers is less as compared to the silicon, and that is the reason why polymers can be used to fabricate disposable microfluidic devices. Disposable microfluidic devices are particularly applied to diagnostic applications, where we take a chip, bring a sample from a specific individual and test it, and then dispose the chip. Okay. So that is called disposable applications of microfluidic chips. The different fabrication techniques that are available to make polymer based microfluidic device are injection molding and embossing and lithography. Okay. In injection molding, we will have to make a replica of the structure, negative of the structure that we want to make, and pressurize molten material, polymer material into that mold cavity, and then we can cool it down and remove the polymer from the mold. Okay. That is the injection molding process. In hot embossing, we have to make a master of the microfluidic structure that we want to fabricate, and from the master we can mold the specific polymer that we are interested in to create the microfluidic structure. Okay. And in lithography, similar to photolithography in silicon, we can use some photoresist to pattern different structures, create channels on the surface of the polymer. Okay. The next material is glass. glass is also economical and it is optically transparent. Okay. So, and one of the major advantages of glass is biocompatible. Okay. So, when especially in microfluidic applications we are dealing with biological cells, biological objects. So, in substrate like silicon and polymer, these substrates are not very much compatible with biological objects, okay, while glass is very much biocompatible. Okay. There are some special characteristics like electroosmosis. So, special characteristics like electroosmosis which we have discussed is very well exhibited by substrate like glass, okay, which has a negative zeta potential. The fabrication techniques that we use to manufacture microfluidic devices in glass can be photolithography and etching. Okay. So, we can, similar to silicon, we can have photoresist patterned onto the glass substrate and create microfluidic channels. We can also do etching of the glass which would require hydrofluoric acid HF etching in glass to create bulk channels inside glass substrate. Then there are ceramic MEMS where there are ceramic materials that can be used to create microfluidic structures. The advantage of ceramic is that they have got very high compressive strength and hardness. So, those are the two important advantages of ceramic, and for which they can be used in harsh environment. Okay. For example, we talk about a micro reactor, okay, where the chemicals that we deal with are corrosive in nature. Okay. The other substrate may fail to work in this case, whereas ceramic, which is very much resistant to the chemicals, can be used in these applications. Okay. For example, creating humidity sensors for heating, ventilation, air conditioning applications, ceramic is used, ceramics based pressure sensor, temperature sensors, humidity sensors are used for HVAC applications because they have good resistance against harsh environments. Okay. And the thermal expansion of the ceramic materials is similar to silicon. Okay. So, many times the ceramic materials are used for packaging of silicon structures. Okay. So, the devices that are actually fabricated using silicon substrate are packaged using ceramic materials. Okay. Metals are also used to create micro devices. One is that they can actually be used to create the microfluidic device itself. For example, in micro reactor application we can use metals to create micro reactors, and they can also be used to create electrode structure for making electrical contacts in microfluidic device, where we can pattern materials and interface that with the fluidics. Okay. So, there are different metals that are used. Gold, aluminum, chromium and platinum are most widely used. All these different materials differ in terms of their properties. The metals have very good reliability, and the fabrication method that you use to create metal structures in micro devices are electroplating, evaporation and sputtering. So, here we contrast different substrate based on the cost, the metallization capability and machinability. Silicon has got relatively high cost, but the metallization is good. We can very well put another metal on the silicon substrate, and the machinability is also very good, okay, because the fabrication method is well understood. So, silicon is the machinability of silicon is very good. Glass has got low cost, but we can easily metallize on glass, we can easily put an electrode on glass, but the machinability of the glass is poor. We need hydrofluoric acid based etching to create microchannels in glass, which requires an expensive setup. Okay. So, the machinability, also the etching process itself is very slow. Okay. So, the machinability of the glass is very poor. Polymers on the other hand are they have low cost, and the metallization is poor. Okay. It is very difficult to put a layer of metal on a polymer like PMMA or PDMS or COC, very difficult to put a metallized layer on the surface of the polymer. And the machinability is fair. We can use established fabrication processes like hot embossing, molding to machine polymers. Ceramics have got medium cost, but the metallization is fair. They can fairly be machined using the established fabrication process. They can easily be metallized using the established fabrication processes. So, easy to put a metal layer on the ceramic surface, but the machinability is also poor like glass. Okay. Here are some of the examples of different metals that are used to fabricate microfluidic device. Here is an example where a silicon chip is used to separate DNA, and the second example where a glass microfluidic chip has been used to sort cells microfluidic inside microfluidic channels. Here is an example where cyclic olefin copolymer, which is a polymer that has been used to analyze proteins, and here is an example of where metals have been put in micro devices. So, this is a thermal actuator where we use gold as the metal in the device, and here we see a ceramic substrate which has been used to package a piezoresistive pressure sensor. Also ceramic has been used to create pressure sensors. Now let us look at what is the difference between MEMS and the IC fabrication, where the MEMS originated from. Typically if you look at here, the semiconductor devices have got relatively smaller size as compared to what we normally encounter in micro devices. Okay. So, the device size in microfabrication is much larger than what we encounter in the integrated circuit. Okay. And the other thing is that the aspect ratio of the different structures that we encounter in micro devices, for example height to width ratio, is much higher as compared to what we encounter in case of the semiconductor fabrication. So, the aspect ratio in case of micro devices is much greater than that of in IC fabrication, and in micro devices many times we have to fabricate layers with gaps between them. For example, we have to create a cantilever based sensors, or a micro channel itself we would always have a gap between different layers. Okay. So, that is a uniqueness in microfabrication which we may not encounter in IC fabrication. So, next we talk about clean rooms. Clean rooms are the environments where we fabricate these micro devices. Okay. So, clean room is nothing but the environment for microfabrication. Okay. So, clean room is the environment for microfabrication where the level of environmental pollutants is very low. When we talk about environmental pollutants, we talk about dust, airborne microbes, aerosols and chemical vapors. So, these pollutants are very low in a suitable environment that we call as clean room. Okay. And typically in a clean room the lighting looks yellow. This is because we remove the shorter wavelengths, namely the UV light waves from the electromagnetic spectrum. Okay. So the UV shorter wavelengths, for example UV, is taken out from the light, so which makes the light look yellow inside the clean room, and that is required because inside clean room we use the UV light to selectively expose and harden the photoresist. Okay. So in order for the photoresist to get exposed to the UV light while doing spinning, or before we expose, we use yellow light. Okay. So clean rooms are classified from class 10,000 to class 1, depending on how good we are at taking out the airborne particles or contaminants from the environment. So a typical urban environment will contain about 35 million particles per cubic meter, and here in the table we see the clean room standards, class 100,000 to class 1. A class 10,000 would contain 10,000 particles that are greater than 0.5 micron, okay, per cubic feet of the air, and a class 1 would contain only one particle that are greater than 0.5 micron per cubic feet of air. So that is the level of cleanliness that we talk about when you talk about clean rooms. Okay. So now let us talk about how we make silicon wafers. So this is a procedure that is used to create electronic grade silicon. First we take quartzite and place it in a furnace with a carbon releasing material, and the reaction happens in presence of heat to produce what is called the metallurgic grade silicon, MGS, and carbon monoxide. Then this metallurgic grade silicon reacts with hydrogen chloride to produce trichlorosilane and hydrogen, and then the distillation of this this trichlorosilane and when it is reduced with hydrogen would produce the electronic grade silicon. Okay. So when the trichlorosilane is reduced with hydrogen, it would produce silicon and hydrogen chloride. Okay. So this is the procedure that is used to make electronic grade silicon, and here is the process that is used to create the single crystal silicon. So we take polysilicon and melt it in a graphite crucible, and then we introduce what is called a seed layer. So the seed layer will have the crystal structure of which we want to create this silicon ingot. Okay. So this seed crystal will touch the surface of the molten polysilicon, and this seed layer will be rotating, okay, and then this is gradually pulled upwards. Okay. When it is gradually pulled upwards, the molten polysilicon will bound to this seed crystal and tend to grow on the seed crystal, and then finally when it is pulled up we get an ingot sort of configuration, and this ingot is cooled and it is sliced and polished to form the wafers. Okay. And you may notice that here we are talking about doping. Okay. In fabricating silicon wafers we use dopants to modify the electrical characteristics of silicon. So we use different kinds of dopants like boron, arsenic, and gallium, phosphorus, depending on how we want to control the electrical properties of silicon. So here is a process which is used to fabricate the single crystal silicon what we discussed in the previous slide. It is called Suralski process. So essentially we have the molten metal present here, okay. So this is the molten polysilicon that we talked about in a graphite crucible, and here we would have the seed crystal which will be rotating, and it is gradually pulled upward. So we would have this the polysilicon, molten polysilicon growing on the seed crystal, forming sort of an ingot, okay, and this ingot will be cooled, which will be looking something like what we see here, and that will be sliced using a wafer saw to create these silicon wafers, okay. So if you look at the silicon crystallography, there are about in nature we have about 14 types of crystal structures that are available, and these crystal structures are known as space lattices or Brevis lattices, and they are classified into 7 different crystal systems: cubic, orthorhombic, rhombohedral, tetrahedral, monoclinic, triclinic and hexagonal. So among these the cubic system is of interest to silicon, okay, and this cubic system would compose of 3 space lattices. One is a simple cubic, SC, BCC is body centered cubic, and the third one is face centered cubic. And these cubic structures are not very well packed, there is always space between the atoms, and that is to accommodate any impurity atoms, okay. So this the cubic structure is not very well packed, can always accommodate the impurity atoms. And the silicon exists in 3 different forms. One is the crystalline, which has got a definite crystal structures, or polycrystalline or amorphous, okay. And it is the single crystal silicon wafers that is used to create micro devices, okay. So single crystal silicon wafers are used as substrate material for micro device fabrication. So if you look at the crystal of silicon, it is basically formed by 2 interpenetrating FCC lattices, and here you see the 3 different lattice structures we talked about. This is the simple cubic lattice structure, where we have the atoms present at the corner of each at the different corners of a cube, and in body centered cubic we would have atoms present at the corners of a cube, and additionally we have an atom at the center of the cube, and in face center we would have the atoms at the corners as well as at the face of each of the faces of the cube, okay, and we will also have one at the center. Now the lattice structure of the silicon is viewed as if 2 interpenetrating FCC lattices. So 2 FCC lattices has penetrated into each other, as we can see here, okay. So in doing so, this is the crystallography structures that we get for silicon, okay. So let us talk about the silicon wafers. By wafer we mean thin slice of material. So the silicon wafers are thin slices of materials of silicon crystal, and we can also use wafers for other materials like polymers, glass and ceramics. So they are basically thin slices of materials of specific size that we use to create micro device, okay. So the silicon wafer serves as the substrate, okay. So the silicon wafer serves as the substrate, and we build structure either over the substrate or under the structure depending on the fabrication process. So for example, if you want to create some electrode structures, you have to create the structure on the silicon substrate. If you want to create a channel by using bulk micromachining, you will have to create the structure inside the substrate. Okay. So there are different fabrication steps that the wafer goes through, for example doping, etching, deposition and photolithography. So we will look at each of these steps in detail. Talking about the size of the silicon wafers, the size may range from 2 inch to 12 inch, and for each size of the wafer there is a thickness associated. For example, a 4 inch wafer will have a thickness of 525 microns, so it is about 0.525 millimeter. So on the right you see some photographs of silicon wafer. Here you see how the wafers are stacked in a box. It is known as cassette, silicon cassette, and here on the right hand side you see a single silicon wafer held. Okay, so the crystal plane is very important in when you talk about silicon wafer, the crystal plane is very important for the electrical and etching properties. Okay, so the electrical and etching property of the wafer would depend on the specific crystal plane, and the crystal plane is defined by what is called Miller indices. Okay, so the crystal planes are defined by Miller indices, and here we see the Miller indices for a simple cubic crystal. Okay, we talked about simple cubic crystal, and here we see the Miller indices for a simple cube structure. So this is the 100 plane, okay, and this is the 110 plane. In fact, here we have two 110 plane. This is 110 and we have one more 110 plane here. Okay, so this plane is also 110, and here we have the 11 plane. So different crystallographic planes are denoted by the Miller indices. Okay, and here we have two different planes. So one crystal may have many different specific planes. For example, here in this case we are talking about two 110 planes in a simple cubic crystal. Here we see 4 of the 8 equivalent 11 planes. So typically there are 8 different 11 planes that are possible in the 11 family of planes, and here are 4 of those shown. So it is basically the plane connecting these two here and then connecting the third vertices here. Okay, and similarly we can have these opposite diagonals connected and then connected to this vertex there. So if you create planes in this manner, we would get 8 different planes, 8 different 111 planes, and 4 of such planes are shown here. Now just by looking at a wafer, we should be able to tell what is the type of the wafer that we are talking about. Now we have here 111 N type wafer. The N type wafer would have a primary flat. Okay, so this is one flat, and there would be a secondary flat here. Okay, this is another flat, and the two flats are located 45 degree to each other. So you can tell if we look at a wafer, the top surface of the wafer, and if we say that there are two different planes which are located 45 degree to each other, we can say that is a 111 N type wafer. Similarly, we can have 111 P type wafer. So N and P are coming from the doping, which we will talk about in the due course. So 111 N type, 111 P type. How do you differentiate 111 P type? Will have only one primary flat. Okay, so 111 P type will have only one primary flat, whereas the 111 N type will have two different flats at 45 degrees. Then we have 100 N type. in 100 n type we would have two flats, okay, one primary one secondary flat located 180 degree relative to each other, okay. And in 100 p type we would also have two flats, but they are located 90 degree to each other. So that is how, just by looking at the top surface of the wafer, we should be able to what is the type of the wafer that we are talking about, okay. Now here we just take a 100 wafer, and here we define different planes. In a 100 wafer, the flat, the primary flat is shown here. This is the 110 plane, okay. This flat is 1110 plane, and then perpendicular to this plane we would have another 110 plane, okay, and at an angle 45 degree to 110 plane we would have two 100 planes, okay. So these are planes. So perpendicular at an angle 45 degree to 110 planes we will have two 100 planes. So these two planes are at 45 degree to 100 planes, and then we would have another one on the surface of the wafer, which is of course the 100 plane, which is perpendicular to this flat, okay, this flat plane. So that is the reason why it is called 100 wafer, because the top surface is 100 plane. So with that let us move on and talk about the basics of photolithography, okay. So photolithography is a process that is used to fabricate micro devices using the characteristics of light, okay. So in this case we use light waves like UV light to selectively cure part of the structure while etching the others to create a specific pattern, okay. And the pattern comes from the mask that we will be talking about. So according to the structure of the pattern we would create a mask and expose the light through the mask to create the pattern of the structure. So the first step is the creation of the mask, which as I said would depend on the structure that you want to fabricate. And for example, if you want to create a channel like structure, as you can see here, depending on the photoresist that you want to use, you may have a mask which would look like this. So these areas may be opaque to light, okay. So if you know what the edge structure that we want to obtain, accordingly we can design our mask. Then the first step it starts with is wafer cleaning, where we try to clean the wafer, make sure that it is free from dirt, dust, any organic deposits, and is perfectly clean, so that the photoresist adhere perfectly well to the surface, okay. So we start with wafer cleaning. In fact, before we go to spinning photoresist, we do oxidation, where you grow a layer of oxide on the silicon wafer, and oxidation is done many times to electrically insulate different metallic layers on the surface of the wafer from silicon, okay. Silicon is semiconducting. So if you want to create an electrode pattern, for example, on the surface of the wafer, we would use a silicon dioxide layer so that these electrodes are not short circuited, okay. And in some cases we use silicon dioxide as a adhesion layer between the substrate and the photoresist. So photoresist will stick much better to the silicon dioxide layer as compared to the bare silicon, okay. So that is the why we need to oxidize the wafer. We will talk about how oxidation is done, and once we oxidize the wafer, the next step is to do the photoresist spinning, okay. So this is where we grow a layer of oxide on the silicon wafer, so typically less than 1 micron, and then we coat a layer of photoresist, okay, which is sensitive to light. Okay. So depending on the depth of the structure, we would control the thickness of the photoresist, and after the spinning of the photoresist, then we will go for exposure of UV light, okay, and we do expose the UV light through a mask, okay, depending on the pattern that you want to create. So let us say here in this case this is a negative photoresist, okay, it is a negative photoresist. So if it is a negative photoresist, all the exposed areas, so these areas of the mask are transparent to UV lights. So these areas of the photoresist get exposed to UV light, they cross link with each other, they become hard and they do not develop when we go through the development process. So here we expose through the mask and then we go for development. So in development, depending on the exposure process, considering that is negative, the exposed areas will retain when they go through the development process, and the unexposed areas will clean away when we put this wafer in a developer solution. Okay. The next, after we develop the SU8, the photoresist layer, then we may have to many times create electrode structures. Okay. So we go for metallization. So around those areas which are where the photoresist is removed, we can create metal structure on the silicon dioxide. Okay. And in some cases after the development stage we go for etching. Okay. So in this case, for example, after the photoresist is developed, we are etching the silicon dioxide layer. Okay. So silicon dioxide is typically etched in hydrofluoric acid and combination of hydrofluoric and ammonium fluoride. So after the silicon dioxide etching, what we go for is resist stripping. Okay. So this photoresist is used as basically a mask layer in this case to etch silicon dioxide, and once the silicon dioxide is etched, we remove the photoresist because it is not needed anymore. Okay. So the silicon the photoresist layer is stripped off, and then here in this particular case, this silicon dioxide, which is patterned because we have etched silicon dioxide around here, is acting as a mask for etching the silicon. Okay. So silicon dioxide is acting as a mask to etch silicon. So here silicon is etched using micro machining, bulk micro machining. Okay. So once let us we have a channel, create an open channel like this, and then we want to use it for microfluidic application. So you would have to bond this with another planar wafer. So we take another planar wafer on the top and bond it with this wafer, so that we get a sealed channel. Okay. So this is done by substrate bonding, and then we go for dicing and wire bonding. Okay. So typically on a single silicon wafer we create many such micro devices, and once these micro devices are all identical, but because to utilize the space available on the surface of the substrate, we use many of these devices on a single wafer, and then to separate these individual devices we go for wafer dicing. Okay. So we dice the wafers, and in some cases we need to establish electrical contact between the external supply and the electrode on a specific device. Okay. For example, if you have a microfluidic device which also integrates an electrode, you have to make electrical contact between a particular location of the electrode with an external point. You can do that using what is called wire bonding. Okay. So, you would use wire bonding to do that. Now, let us look at the first step of fabrication, which is called the mask creation. So, typically a mask looks like this. This is a photolithography mask. It will have pattern depending on the structure that you want to create. So, the patterned areas, all those black areas that you see here are opaque to light. Okay. So, they do not allow light in those areas of the mask. Okay. So, mask is nothing but it is a stencil to repeatedly create pattern on a resist coated wafers, and these masks are optically flat because they have to be put together with the surface of the substrate, which is flat, and this the material that we use to generate this mask is typically optically transparent. So, they can be transparent to UV light, and the dark areas that are opaque to light can be created using different materials. For example, chrome is one material that is typically used to create these opaque structures, patterns on the mask. And when we design a mask, another important thing is to have the alignment marks, what we call it as crosshairs. Okay. So, when we do multi-layer photolithography, for example, we do patterning of one layer, and again we go for putting the photoresist and exposing the UV light, then we would have to make sure that the second layer is registered properly with respect to the first layer. So, you would need to align the mask. Okay. And for the mask alignment, we need to have these alignment marks or the crosshairs. So, this is an important feature of the mask design. Now, to create these opaque patterns or the observer patterns, we use what is called e-beam lithography. Okay. So, we use the mask for photolithography, but to create the structure or the pattern that is used in photolithography, we used a more sophisticated technique called e-beam lithography, which is called higher resolution than the photolithography. Okay. And this is ensured because we would have the design of the mask. So, using a CAD software, it can be converted, and we can ask the e-beam writer to write mask on a specific material. Mask can be categorized as hard mask, okay, or soft mask. Hard masks are expensive, okay, because we use a material like quartz or glass to create these hard masks, and the resolution of the hard mask is typically much better as compared to the flexi mask. Okay. And we use e-beam lithography to write this high resolution mask. Flexi mask on the other hand are cheaper. They can be simply printed on a transparency sheet, and the resolution is typically poorer as compared to the hard mask. Now, let us talk about mask polarities. The mask polarities can be either light field or dark field. Here is one example of what we mean by mask polarity. Let us say our CAD software is giving this sketch here. So, we want to write the word MEMS on some kind of pattern on silicon wafer. So, we create this CAD design where MEMS is written. If we ask we define the dark field mask, okay. If we tell the vendor who is printing the mask, for example, to create a dark field mask, so this is the mask that we will be getting. Okay. So, the later patterned areas here in this case, in the dark field case, is transparent to light. On the other hand, if you ask for a clear field mask, this is what we get, the patterned areas become opaque to light. So, this is very important to understand when we design a mask, and we ask a vendor to print this mask. It is very important to mention whether we are going to print it as dark field or we are going to print it as clear field. Okay. Now the masking methods, once we have the mask and while we are doing the UV exposure, there are different techniques that are available. One is the shadow printing and the second one is projection printing. In shadow printing, the mask is relatively closer to the surface of the substrate, and in projection printing the mask is little bit far away from the surface of the substrate. Okay. And in projection printing we would have a optical system between the mask and the substrate, so that the resolution can be further improved by adjusting the numerical aperture of the optics. Okay. Again the hard contact mask. So in hard contact the mask and the substrate are in physical contact. Okay. So you can actually, we are putting the mask in physical contact with the substrate, and this is typically used in R&D or in academic environments where the variability of the mask is not a concern, because it is coming in contact with the photoresist. Over a period of time there would be scratches and wears would be developing on the surface of the mask. So and in soft contact, in hard contact there will be physical contact, in soft contact the mask will be actually lifted about 20 micron above the substrate, and this is also known as proximity mask, where the mask is not actually in physical contact, but there is a gap between the mask and the surface. In projection printing we are using a high resolution optics system. Typically 1:10 reduction is possible to improve the resolution. For example, if you want to create a feature which is 1 micron in size on the substrate, we can create a mask that has a line width of about 10 micron, and still we will be able to do that using the lens system that will provide 1:10 reduction. Okay. So 10 micron on the mask will appear as 1 micron on the feature. Okay. And in this case, since we are not talking about physical contact between the mask and the substrate, the lifetime of the mask will be very good. So let us look at the resolution of the contact printing. In contact printing where either we talk about hard contact or soft contact, the resolution B would depend on the wavelength lambda, okay, and the distance between the mask and the photoresist layer. Always, even if in hard contact, there will always be a gap between the mask and the photoresist layer. So that would also affect the resolution in addition to the wavelength. Okay. So this is the formula that we can use to find out the resolution of the pattern if you know the wavelength and the gap between the mask and the substrate. Okay. So what we see here is the resolution is highly dependent on lambda, okay, and it is difficult to go for a feature which is considerably less than the wavelength. However, in projection printing the resolution can be decided or controlled by adjusting the numerical aperture of the lens system. So B will be equal to lambda over 2 into numerical aperture. So you can control the numerical aperture of the lens system to control the resolution of printing in case of projection printing. Once we fabricate the mask, the first step would be once we fabricate the mask and we have the wafer ready, the first step would be to clean the wafer. And the wafer, some of the wafers that we can order from manufacturers, they already come clean, and we can order depending on the size of the wafer that we want, and also in some cases if you are interested in the electrical properties, we can also control the doping of the substrate that we order. And many times we can also go for wafers with which have already a thin film of coating. For example, on a silicon wafer, if you want to have a oxidation layer, then already we can ask for a specific wafer with some thickness of oxide layer on it. Okay. So in any case we have to clean the wafer. Typically there are different procedures available to clean wafers. RCA1 and RCA2 cleaning protocols are widely used, and although there are other methods like wafer cleaning, ultrasonic agitation, and plasma polishing, which is a dry cleaning procedure. So RCA1 and RCA2 are widely used for cleaning wafers. In RCA1 we would be mixing 1 part of ammonia with 5 parts of DI water and heat them to boiling temperature, and then we add 1 part of hydrogen peroxide and then immerse the wafer for 10 minutes. Okay. And that procedure, the RCA1 cleaning procedure, will remove the dot from the wafer. Then we go for RCA2 cleaning procedure, where we mix 1 part of HCl with 6 parts of DI water and then heat them to boiling and then add 1 part of hydrogen peroxide. So here we are using ammonia, here we are using hydrogen chloride, and then immerse the wafer for 10 minutes to remove the metal ions. Okay. So the purpose of RCA cleaning 1 is to remove the dirt, and the purpose of RCA2 cleaning is to remove the metal ions. So this is a typical clean bench that is used for RCA cleaning, and here we contrast wet and dry cleaning. Okay. So there are different attributes. For example, for particle removal, wet drying will be, wet cleaning will be better. So here we contrast wet versus dry cleaning, and there are different attributes. For particle removal we will go for wet cleaning. For metal removal also wet cleaning is preferred. For heavy organics wet cleaning is preferred. For light organics we can either use wet cleaning or dry cleaning. The throughput of the wet cleaning is much higher as compared to dry cleaning, and the repeatability of the wet cleaning is also better. The only downside of the wet cleaning, since we are using the chemicals that are not environmental friendly, the dry cleaning has very good environmental impact. Okay. It is not hazardous to the environment, whereas the wet etching is hazardous to environment. So with that let us stop here. We will continue our discussion on microfabrication later.